Dear children, hearty welcome to today's class. Last class, we were discussing about refractive index, specific refraction, molar refraction, and optical exaltation. Today, firstly, we will discuss some problems regarding molar refraction. Then we will see the surface tension and its relation to intermolecular forces. Now, let us discuss the problems with respect to the molar refraction. The problem is that the refractive index of carbon tetrachloride for D line of spectrum has been found to be 1.4573. Calculate the molar refraction if the density is 1.595 gram per centimeter cube. Here they have given N, that is the refractive index of carbon tetrachloride 1.4573. And our job is to find out the molar refraction, that is Rm, that we have to find out. And the density is given, that is 1.595 gram per centimeter cube. So, all these values are given. Then we have to find out the molar refraction. Molar refraction, to find out the molar refraction, we have an equation. Rm is equal to n square minus 1 divided by n square plus 2 into m by rho. Now, we have to find out the molecular mass of carbon tetrachloride. There one carbon is there, therefore 12 plus 4 into the mass of chlorine is given, that is 35.5. Approximately when we multiply 4 into 35.5, then that will add with that value we are adding with 12. Then finally we will get something like 154 gram per mole. Okay. Then now we have to substitute the values here, that is Rm is equal to 1.4573 square minus 1 divided by 1.4573 square plus 2 into molecular mass, that is 154 gram per mole, we can write like this, then divided by rho, that is 1.595 gram per centimeter cube. Okay, here when we calculate all these things, all the multiplication and division, when we do everything, finally we will get an answer as 26.51 centimeter cube mole inverse. Centimeter cube mole inverse. Here this gram will get cancelled and this gram will get cancelled. Then finally we will get this centimeter inverse. When it goes to the numerator, it will become centimeter cube and mole inverse. Then the answer will be 26.51 centimeter cube mole inverse. I hope you understood this problem. Just we have to substitute the values what is given there, then we will get the answer of molar refraction of carbon tetrachloride. Our next problem is, given that the molar refraction of a liquid is 12.85 centimeter cube mole inverse, calculate the refractive index. Here we have to find out the n value, and they have given Rm, that is molar refraction of a liquid, that is 12.85 centimeter cube mole inverse, then the molecular mass is, that is M, is 60 gram per mole. Density is 1.6468 gram per centimeter cube. The equation to find out Rm is n square minus 1 divided by n square plus 2 into m by rho. We have to substitute everything here. The Rm is 12.85 centimeter cube mole inverse, and n square minus 1 divided by n plus 2 into m is 60 gram per mole, and rho is 1.0468 gram per centimeter cube. And when we substitute all these values and do the calculation, we will get n square minus 1 divided by n square plus 2 as 0.2240. And here is not having the unit because this centimeter cube and this centimeter cube will get cancelled. Then we have here mole inverse, this gram will get cancelled and this gram will get cancelled. Then finally we have n square minus 1 divided by n square plus 2 is equal to 0.2240. That is, now we have to solve this equation, that is n square plus 2 is equal to 0.2240. N square minus 1 divided by, n square minus 1 is equal to n square plus 2 into 0.2240. So here 0.2240 n square is equal to 2 into 0.2240 is something like 0.448. Here we have n square minus 1, then this n square we can take out 1 plus 0.224, then here we will get 0.448 plus 1, then here we will get one answer, here also we will get one answer. From this we will get the value of n square, then we have to take the square root of that value. Finally we will get the answer as 1.36. This is the calculation of this problem. Okay, now let us see the another property of liquid, that is surface tension. As the name says, it is a property which is related to the intermolecular attractive forces at the surface of the liquid. We know that the liquid at the surface is having less attractive forces compared to the molecules which are at the interior. Here it is shown the diagram. Here in the case of liquids, the molecules are arranged like this and there is some empty space between these molecules and there is an intermolecular forces also. The molecule which is at the interior is experiencing the force from all the directions, but the molecule which is at the surface, it is experiencing the force from this direction, this direction, this direction, this direction. It is not getting a force from the up. Then what happened? The molecule which is at the surface will have an inward pull from the interior. It is experiencing, the molecule at the surface is experiencing an inward pull from the interior. Therefore, there will be a tension at the surface molecule. The surface molecule is experiencing a tension. That is called as surface tension. Here we have one figure. Here the molecule which is here is experiencing a force, intermolecular force from all the directions, and the molecule which is at the surface is having only the intermolecular attraction from these sides, not from the up. Therefore, the molecule is having some inward pull. Because of this inward pull, the surface molecule is experiencing some tension, that is called it as surface tension. That the definition of surface tension is due to the resultant inward pull felt by the molecules at the surface, a liquid surface behaves as if it were in a state of tension like a stretched elastic film or membrane. This property is referred to as surface tension. That is, because of the resultant inward pull of the molecules at the surface, the liquid surface behaves as a stretched elastic membrane, and this property is called it as surface tension. Once again I repeat, due to the resultant inward pull felt by the molecules at the surface, a liquid surface behaves as if it were in a state of tension like a stretched elastic film or membrane. This property is referred to as surface tension. We can explain this surface tension in another way, that is, the surface tension of a liquid is defined as the force acting at right angles to any line of unit length along the surface of the liquid. That is, when the molecule is here, it is having, when one line is here, the molecule is experiencing force here, that force is perpendicular to this line. That is what this explanation, this definition, the surface tension of a liquid is defined as the force acting at right angles to any line of unit length along the surface of a liquid. Hence, this surface tension is a surface phenomenon of the molecule in a liquid. From this definition, we can understand that the surface tension is nothing but force per unit length. That is, surface tension is force per unit length. Force per unit length. Therefore, its unit is the unit of force is Newton and the length is meter. Since it is force per length, the unit of surface tension is Newton per meter. That is in SI system. If it is in CGS system, the unit is dyne per centimeter. Dyne per centimeter or dyne centimeter inverse. What is the effect of this surface tension? Because of the surface tension, the molecules at the surface will try to reduce the surface area, and therefore the molecules will experience the reduction of the surface area, or the liquid at the surface will try to reduce the surface area at the surface. The effect of surface tension is to reduce the surface area to a minimum. That is the effect of surface tension. Because of the surface tension, the molecules at the surface will try to reduce the surface area to a minimum. Now, since the surface area is minimum, if one want to increase the surface area of the liquid, some energy is required. That energy is called it as surface energy. That is, the work or energy required to increase the surface area of a liquid by 1 unit is called surface energy. I repeat, the surface energy. the work or energy required to increase the surface area of a liquid by 1 unit is called surface energy. We say that the surface tension is numerically as well as dimensionally equal to surface energy. That is, the surface tension is nothing but the force per length, and surface energy is work per area. That means here it is force by dx. Here work is nothing but F into dx, and area also, that is L into dx. This dx and this dx will get cancelled, and finally we will have F by L. Therefore, we can say that the surface tension is equal to surface energy numerically and dimensionally, since it is force per unit length. Both are force per unit length. The dimensions also will be same. If the molecule at the surface is having high interior pull from the bulk of the liquid, then the surface tension will be maximum. The surface tension of the liquid at the surface depends upon the how strong the interior force, or how much strong will be the inward pull of the molecules from the interior. Therefore, we can see that the greater the surface energy will be there if the molecule is having larger inward pull from the interior. Surface tension of some liquids at 293 Kelvin is given here. The water is having the surface tension of 7.275 into 10 power minus 2. And acetone is having 2.37 into 10 power minus 2. Ethanol is having 2.227 into 10 power minus 2. So when we compare this, the water is having more surface tension compared to acetone and ethanol. This is about surface tension. Surface tension is something like the surface phenomenon, that is the inward pull of the surface molecules by the intermolecular forces of the interior. That is nothing but surface tension. Because of the surface tension, the surface area of the molecules, surface area at the surface of the molecules in the liquid will be minimum. And in order to increase the surface area, the energy is required. That energy is called it as surface energy. And if the inward pull is strong, then the surface tension also will be more. Now, let us see another thing, that is interfacial tension. That is interfacial tension. The interfacial tension is nothing but the tension at the interface. That means the tension at the surface of the liquid between the liquid and vapor phases. The tension at the surface of the liquid between the liquid and vapor phases. That is the interfacial tension. If we define surface tension in terms of interfacial tension, that is, the surface tension is the interfacial tension at the surface of separation between the liquid and vapor phases. The surface tension is the interfacial tension at the surface of the liquid between the liquid and vapor phases. That is, in general, we can see that the interfacial tension is between the liquid and vapor phases, or when two phases are in contact, then the interfacial tension occurs. Now, we have another term, that is interfacial surface energy. We have interfacial surface energy. That is the work required to enlarge the surface of separation between two immiscible or partially immiscible liquids is called interfacial surface energy. That is, the interfacial surface energy is the energy required to enlarge the surface of separation between two immiscible liquids. Immiscible liquids means we can identify or we can see that it is not mixing or it is not that much soluble. One liquid is, there will be miscibility. We can clearly identify the two liquids, that is called it as immiscible liquids, or partially miscible liquids means again we can see, we can identify the two liquids between them. That is called it as immiscible or partially miscible liquids. Interfacial surface energy is the work required to enlarge the surface of separation between two immiscible or partially miscible liquids is called interfacial surface energy. This interfacial tension is less than that of the surface tension. This interfacial tension also operates in solid and liquid interfaces. This is about interfacial tension. So, interfacial tension is tension which occurs at the surface of the liquid when the liquid and vapor phases are come in contact. Now, let us see some application of this surface tension and interfacial tension, that is the cleansing action of soaps and detergents. The cleansing action of soaps and detergents. Here, for cleaning our clothes and all, we use detergents. They are surfactants. Surfactants means surface active reagents or surface active agents. That means these substances which cause a marked reduction in the interfacial tension between water and phase immiscible with it. The surface active agents or surfactants will reduce the interfacial tension between the water and the other liquid which is immiscible. Okay, that is what the surfactants. We have some examples of surfactants. They are sodium stearate. Soaps are nothing but the sodium or potassium salts of fatty acids. Here we have sodium stearate, that is the sodium salt of stearic acid. Here we have sodium lauryl sulfate, that is the sodium salt of lauric acid. And here we have a cationic surfactants, that is cetyl trimethyl ammonium chloride. These all are examples of surfactants. When we look into these surfactants is having a hydrophilic part and hydrophobic part. Here if you look into the sodium stearate as an example, this C17H35 COO minus Na plus is there. This CO minus part, that is the hydrophilic part, and the hydrocarbon part is hydrophobic part of sodium stearate. When we clean our cloth using surfactants, what will happen? The hydrophilic part of this surfactant will attach to the water molecule and hydrophobic part will attach to the grease or oil which is there in our dress. It will be something like this. Here we have our water, and this hydrophilic part, that is, if we take the example as sodium stearate, that CO minus will attach to the water molecule, and the hydrocarbon part will attach to the oil. Then we will have something like this structure. Then what will happen? When it happens, the interfacial tension will reduce. Therefore, there some interfacial layer will form, because here we have immiscible liquid. That means the water and the oil is there. Therefore, this is an immiscible liquid. We can clearly identify water and oil. Therefore, the interfacial tension will lower because of the presence of interfacial layer, and this interfacial layer formation will promote emulsification. Emulsification means mixing of this water and oil. That is something like emulsification, mixing of two liquids. That is emulsification. So when this happens, this colloidal solution will form. When we rub that one, our dirt will remove, or oil or grease will remove from our dress. That is the cleansing action of soaps. There the surface active agents will reduce the interfacial tension between the water and the immiscible liquid, that is grease or oil. Here we have taken examples as the sodium stearate, then we have the sodium lauryl sulfate, cetyl trimethyl ammonium sulfate. Here the COO part is the hydrophilic part of sodium stearate, and that is the sodium salt of stearic acid. This hydrophilic part of this surfactant is attached to the water molecule, and hydrophobic part, that is hydrocarbon part, that will attach to the oil or grease. When it attached to the oil or grease and this hydrophilic part is attached to the water molecule, here this structure is forming. Here it will form like this, and there will be an interfacial layer forms in between the water and this grease. This interfacial layer formation will promote the emulsification. That is why the oil or dirt will remove from our cloth. This is about the cleansing action of surfactants. The main concept or principle which play here is interfacial tension. In this session, we discussed the surface tension, interfacial tension, and the cleansing action of detergents. In the surface tension, we saw the definition of surface tension and the effect. Also, the effect of surface tension is to reduce the surface area to a minimum. Then we saw that what is surface energy, that is the energy which is required to increase the surface area. Then the dimensionally and numerically, the surface tension is equal to the surface energy. Then when we come to the interfacial tension, we saw that what is interfacial tension, that is nothing but the separation, or that is when the surface phenomenon, that is at the surface of the liquid, there is a separation between the vapor and the liquid phases. Therefore, there is a tension, that is tension occurs at the surface, that is called as interfacial tension. And finally, we saw that what is the cleansing action of surfactants. I think you all understood this surface tension, interfacial tension, and cleansing action of detergents. With this, we conclude this session here. Let us see the next class with more properties of liquids. Thank you.